I'm Meghamala, and today I'm going to talk about problem solving on sequential logic. So, uh, so far we have discussed few problem solving in different models, right? In Verilog, we have, as we know that there are 4 different types of modeling styles, and till now we have discussed many problems based on different modeling styles. And today we will be discussing some more problems on sequential logic, which is module 5. Okay, so let's move forward. When should an FPGA CPLD be used? So here, the very first slide, we just know what when we are discussing the module 5, we already studied about the FPGA and ASIC, right? So we have discussed what are the different types of FPGAs and ASICs. What is FPGA basically, and how does it going to work, and also what is an ASIC. And now we will see when should an FPGA or ASIC is used, or CPLD, FPGA or CPLD are used. We know that FPGA is field programmable gate arrays. This is field programmable gate arrays, right? Gate arrays. Then we know that CPLD is complex programmable logic devices, right? Complex programmable logic devices. In FPLD, in FPGA and CPLD, we will see some we'll come across various lookup tables, okay, lookup tables, input output boxes, and so on. So now we will see how this FPGA and CPLD are going to be used in the designing process. So further, the first choice for design with the following exceptions. So when you want to design some module, okay, when you want to design some electrical module in terms of FPGA or CPLD, then you have to consider this criteria with some exceptions. So we will see what are those criteria. So now the first and foremost choice that we have to go with is extreme performance requirement. So the first thing we have to choose is all about the high clock frequency. Okay, so this the clock frequencies will help us to give the better performance. Okay, then will be produced in massive quantities. So the second choice is when you are going with this FPGA or CPLD, it means that you are producing some large amount of large quantities of designing that you are doing. Okay, though it is complex, but still you are giving an attempt to produce a massive quantities. And then the third is it's very complex design. So we know that FPGA is a field programmable gate arrays, where in this FPGA will be there are more than 10,000 of gates are used. Okay, there are more than 10,000 of gates are used, so that we are calling it as a complex design. So it's a complex design, very complex design. Very large FPGAs are expensive. As the number of gates are increases, what happens is it will be more expensive, right? So it will be more expensive, and the designing is also very complex. Then analog electronics needed on the same chip. So some devices which are based on the analog electronics, they are purely dependent on this FPGA chip. Then designs where low power is critical, that is mobile applications. For the mobile applications, maximum we won't use this FPGAs. So the designs where low power is critical. So for the less power consumption devices, basically we don't prefer this FPGA designings, right? Then ASICs design is prototyped on FPGA, okay, and conversion to ASIC is outsourced if the company lacks dedicated ASICs designers. So here we are seeing some relationship between FPGA and ASIC. Okay, FPGA and ASICs. We are saying that the ASIC design is prototyped. Okay, it is designed in such a way that the FPGA involvement will be there in the designing of ASICs, right? So the company is dedicated to the ASIC designers in such a way that the FPGA involvement is purely seen if you are designing your product in terms of ASIC designing. Okay, then ASIC versus of FPGA projects 2003. So here in this in 2003 year, they have produced some product where it has 1500 to 4000 new ASIC projects each year. So from 2003 onwards, we are seeing that in the market 1500 to 4000 new ASIC projects are releasing, right? Then 450, what is this, 450,000 new FPGA projects every year. So if you see the difference between, or else if you see the separation between ASIC and FPGA, we are seeing that more than the ASIC projects, we see there is an immense increase in the FPGA projects, right? So this is a simple statistics based on the improvement in the ASIC and as well as the FPGA projects. Then main advantages of FPGA development over ASIC. So here we will see the advantages, or else we see some development based on the ASIC over FPGA. Then lower economical risk with a much lower initial investment, that is non-zero recurring engineering cost. We see the advantage of considering FPGA over ASIC is, the first thing is lower economical risk. So here we see there is a less number of economical risk. Okay, so if you consider FPGA, if you are allowed to do your project, or else if you are allowed to do a designing in FPGA, it means that it is very cost effective. Okay, so here non-recurring engineering cost. Okay, the cost will be very flexible. Lower economical risk you will see if you are designing your product in FPGA. And then shorter development time due to easier reprogramming, result in faster time to market. So if you are able to do your, if you are coming up your project with in terms of FPGA, first thing is it is economical. We see that there is a lower economical risk, first thing. Then the second thing is it's all about the shorter development. In very short time you will see a huge development. Okay, we will see here immense development in the programming of this particular FPGA. Then SRAM and flash based can be reprogrammed both during development and in system after delivery to the customer. So after delivering the product to this customer, we see the flash based can be reprogrammed. So there is an option to reprogram the project as well. Okay, so there is an option, or else there is a flexibility to reprogram in terms of SRAM and as well as the flash based memory. Okay, so these are the few advantages that of FPGA over ASICs. Then, so now we will see how FPGA to ASIC. If we move on from FPGA to ASIC, what sort of development we see? Okay, what sort of changes we see? Now, one or more FPGAs are used for prototyping and ASIC design. So just remember that we have two designing ASIC and FPGA. So in order to design this ASIC, you have to remember that the involvement of FPGA is seen, right? So one or more FPGAs are used for prototyping the ASIC design. So in order to prototype this ASIC design, in order to reframe this ASIC design, we see two or more FPGA programs are used. Then a challenge that ASIC does not have the same blocks of the FPGA. So if you observe, or else if you compare this FPGA and ASIC, we see the challenges which are overcome, or else the challenges that we see in terms of ASIC, they does not have same blocks in FPGA. So that means what? In a simpler way, I can say that in every module, or else in every area, in every corner of the area, we see there are some challenges to face, right? So in this ASIC and FPGA designing, there are more challenges to be faced by ASIC. If you are considering, or else if you are considering your product to be made in terms of ASICs, then remember that there are many challenges to be faced, okay, rather than the FPGA. So that's what this sentence says, that the challenges that ASIC does not have the same blocks as FPGA. So whatever the challenge that you are facing with regard to the ASIC, you may not see the same changes followed, or else you may not see the same challenges which are occurring in the FPGA. Less number of challenges can be seen in the FPGA. Then a library can be made of functions, multipliers, memory blocks, etc. that exist in an FPGA to allow to use an ASIC. Through this limits the ASIC synthesis. So if you are programming your product in the ASIC designing, okay, then the synthesis has to be done to that particular product. and that synthesis has to be done with respect to the FPGA. That means what here, for every module that you are synthesizing, remember that there is a library, okay, and that library contains all sort of elements that you are considering in order to design some module. So that library, it may contain some multipliers, it may contain some memory blocks, and it may contain the gates as well. Okay, so for each and every module synthesis, see, when the synthesis in terms of ASICs or the synthesis in terms of FPGA, you have to remember that all for the synthesis, the elements which are needed for the synthesis can be taken up from the library. Okay, Verilog library. Then the RTL code should be the same for both ASIC and FPGA. So the code which is needed to write for the programming of this both, they are same. The RTL code, register transfer level, the code which is pertaining to this FPGA and ASICs are both the same. There is no change. And then one example we'll consider here. So in this example, on semiconductor and Intel, that is Intel offers implementation of FPGA based solutions in ASICs for high performance, low production price and low power consumptions. So here, this particular semiconductor or Intel, okay, they are providing some products. Those products are having the less consumption, power consumption will be less, and low power production, the power production price will be less, and we see the higher performance. Okay, so and then also the original ASIC is out of production. So when we observe the ASIC and FPGA, we see there is a huge amount of advantages. That's a huge advantages huge advantages we can see in terms of FPGA rather than ASIC. So here also original ASIC is out of production, and the expand functionality of an ASIC without a new large investment, that is FPGA development, is much cheaper than ASIC development. So this is a very important point, and it's a very basic point if you compare these two designing, that is FPGA and ASIC. So when you compare this FPGA and ASICs, we see that FPGA is very cheaper. It is easier to construct and the power consumption will be very less, and we see there is a high efficiency. The overall efficiency is maximum in the FPGA designing if you compare with this ASIC design. That's what it's saying. So FPGA development is much cheaper than ASIC development. Then the size of modern FPGA have made it possible to implement ASICs made a few years ago in a single FPGA chip. So in the single FPGA chip, we can see the accumulation of all the peripherals which are assigned with respect to the ASIC design. Okay, and then requires updating the ASIC design to adapt FPGA specific functionality and features. Okay, so for example, in the archaeology, we can see that there are many things to sort out, right? So in that many things, we can see that it requires updating the ASIC design. The FPGA, it requires the updations from the ASIC designs. Okay, updations from the ASIC design is needed, very much needed, and also the functionality based on the FPGA specific is also much required along with the features. Then now we will see the coding styles. So in the FPGA and CPLD, we have some coding styles to perform and as well as the pipelining. So coming from the coding styles, so the coding styles goes with the pipelining, number of logic levels, asynchronous logic, use of clocks and latches and the registers. So these are the few coding styles that we can see if you are moving your design from ASIC to FPGA. Right, so we are moving from ASIC to FPGA. So when you are moving your designing from ASIC to FPGA, there are some protocol that we need to follow. The first and foremost thing is all about the coding styles. So the coding styles will contain, that means what the coding part can contains all the elements, that is pipelining, number of logic levels, latches and registers, and use of clocks and as well as the asynchronous logic. Okay, so first thing we will see about the pipelining. So the pipelining, it says that, see here for example, we are considering a washing machine. So washing machine, see we have wash 1, 2, 3. So this is in this one pipelining and this is second pipelining. In the first pipelining, there is a timeline given. So at 17, right? At 17, what are we doing? At 17 to 19, we are just this washing machine, we have to set. Okay, that means what? It has to rinse, it has to wash out the dust, and it has to rinse, and it has to dry, right? So all these three categories, all these three tasks, the tasks should be done in this time level. For example, let's say T1. Okay, then after this, the second time 2, at time 2, again it has to perform all the three tasks. Okay, and then finally at time 3, it has to perform all the three tasks. But how it is performing? For the first wash, in the wash 1, it will just take out this surf or the detergent, and then the second it will rinse, and in the third it just dries out, right? First it consumes the detergents, and in the second pipeline, or else in the second time period, what it will do is it just rinse, and in the third time period it just dry out the clothes. So this is how the pipelining works, that right? So, and then for example, this is a second in the second timeline, we will see there are wash 1, 2 and 3. So here if you see that there is an overlapping of the timings can be seen. So in the first wash, we see that in the time 1, the first wash should be done, right? But what happens when it comes to the second wash? Simultaneous, that means what? Parallelly it is doing, right? So parallelly at the time T2. So this T1, it's divided its time to T11, T12 and T13. So what happens here? We see at T11, we see the task 1 is completed. Okay, consuming the detergent from the consuming the detergents is done at time T11, and at time T22 we see it start the second task, that is rinsing, and at time T3 it started the drying part it started. So this is how the pipelining mechanism we can see when you are comparing this ASIC to FPGA. So this is one of the coding style that we can write our code in terms of, that is what we can write serially, sequence wise, or else we can write parallelly. Okay, serially and parallelly we can write the code. Coming to the pipelining in digital system. So this is the pipelining in digital system example. This figure clearly talks about, see here we have the data in, and we have the data out. That means what? This is a transmitter, for example, you can consider, and it's a receiver. So at receiver, at the transmitter, I'm sending some data, and that data has to reach the receiver at some particular time. Okay, with some time delay, that receiver has to receive the data from the transistor. So that receiving of data can be done in terms of some time delay. So let's say that T1, T2 and T3. Okay, so these are the combinational logic. So the pipelining is done, we are considering in terms of some digital systems, and that digital systems are some data that I'm sending, and the receiver has to receive the data, and the receiver, it has to receive the data in regular time intervals like T1, T2 and T3. So for example, here we have time 1, time 2 and time 3. So the data in with respect to the clocks. Okay, so with respect to the clock 1 and also the registers. The registers contains all the information, the data which is needed, and it accumulates. The register is nothing but it's a combination of both latches and flip-flops. It stores some data of information, right? So that data that we are sending from the transmitter to the receiver in regular intervals of time. That is what the pipelining talks about. So at time T1, I am sending some information. That means what? Here I have to send 20 bits of information. Okay, this 20 bits, what am I doing is 30 bits of information I want to send from the receiver to the transmitter. So at the receiver, I should receive 30 bits of information. So how am I sending is, I can send at time interval T1, I am sending 10 bits of data. Okay, and see, I told you the pipelining can be done, or else a pipelining can be achieved using two scenarios, that is synchronously or serially, and the second one is parallelly. So that's why we are calling it serial pipelining and as well as the parallel pipeline. In both the ways, in either the ways, we can send the data from the transmitter to the receiver. So here in this particular example, I have the clock times and I have to send the data in 3 regular time intervals, that is T1, T2. Okay, or on 2 timings I have to send the data. So what I have to do, so I'm considering my 20 bits of data. So at time T1 I can send my 10 bits of data, and at time T2 I can send my another 10 bits of data. So overall 20 bits of data at regular time intervals T1 and T2 I am going to achieve it. So this is what the pipelining in digital systems. And now we will see the number of logic levels. It is one of the category. Okay, this is one of the category that we see if your designing is from FPGA to ASIC. Okay, if you are FPGA to ASIC. So the next is number of logic levels. So this particular example talks about the logic levels from previous bank of registers to the next bank of registers. So here we have 3 levels of logic. So what are those logic? And, or, and, not. We know that we represent and with and, okay, ampersand, or, and, as well as the not. We know the gates, okay. So and gate, we know the how can we write the Boolean expression for this and, or, and not. So the number of logic levels here, if you observe, there are 3 logic levels. So the number of logic levels are more critical in FPGA, where the delay between ports often are higher than ASICs. So here, the number of logic levels in FPGA is bit critical. Okay, that means what? The consideration of this number of logic levels is reduced. We can reduce the number of logic levels consideration in FPGA because we see there are higher between the there will be a delays. Okay, the delay, we can see the abrupt delays can be arised if you are switching on from one logic level to the other logic level. And FPGA designs may use more pipelining than ASIC designs. So we can say that this is one of the one of the criteria where there is no where it is having many disadvantages, right? So in FPGA, with regard to the number of logic levels, we are saying that we use more number of pipelines than ASIC designs to achieve the required clock frequency, since each logic cell in FPGA contains both LUT and registers. Yes, obviously in the FPGA design we see LUT. LUTs are nothing but the lookup tables. Okay, so this lookup tables we have, and also we have different types of registers as well. So the connection between these two lookup tables and registers, the complexity will be maximum. So that's the reason the disadvantages that we can consider this as one of the disadvantages of the FPGA. Then coming to the clocks. In the clock, limited number of clock distribution network in FPGA limit the number of clock domains. So as we say that if you compare FPGA and ASIC, FPGA is more convenient to consider, right? And one of the thing in terms of clock is we say that there are limited number of clock domains are considered in the FPGA. And general FPGA inputs can often not to be used for clock signals. So general FPGA designings, we see that the clock designing, we see that the consideration of clock designing is not that needed. Okay, then FPGA designers do not need to tune clock paths. So there is no need to ponder more on the clocks. Okay, the place and route tool for FPGA automatically does this. So inbuilt the FPGA designings, they have automatically they route and also they connect. Okay, they connect the devices and parallelly they just synthesize the program. Okay, this is what we observe in FPGA. And clock enabling and not clock gating should be used in FPGA. So in the FPGA pertaining to this clock, we see the clock enabling can be done by itself by default, and then clock gating can also be done. Clock enabling and clock gating is also done by within itself in this FPGA, but only using special clock gating cells. So the clock gating can be done only with the help of the special. There are some special gating cells are considered in this scenario. So in the clocks, so the only that particular clock gating signals only can be considered. So here they have given, for example, a buff CGE. That means what? Clock buffer from Xilinx. So this resembles that there is a clock. The usage of clock gating. So for clock gating purpose, I can go from the I can go with this buff CGA. Okay, and due to limited number of clock gating signals, this buff CGA should clock gating be used for clocks to one or more modules. So as we have limited clock signals, so only that limited clock signals, only that considered clock signals can be given to other modules as well, or other modules as well. So these are the few problems. So so right from starting till the end, we have observed one thing, that if you want to design your particular product in FPGA, it is more convenient to design your product in FPGA rather than ASIC. Why? Because FPGA is having more advantages if you compare with the ASIC. One of the more advantageous things that you consider in the FPGA is clock. Okay, clock and parallel pipelining. Clock pipelining. Okay, clock pipe. I can say clock signal pipelining are the two major things that you can consider if you are going to design your product in the FPGA. And one of the disadvantages that you can consider in FPGA is number of logic levels. So if your number of logic levels are increasing, what happens is there is a complexity. Why? Because that complexity arises because of the delays. As more number of logic levels, more number of gates increases, what happens? More delays occurs. As more delays occurs, what happens is the efficiency decreases. So this is, I can say that the number of logic levels, this category it degrades the designing of FPGA in the designing. And also, these are the coding styles we have discussed: pipelining, number of logic levels, use of clocks, latches, and the registers, right? And also, you have to remember that if you are switching your designing from ASIC to FPGA or FPGA to ASIC, so from ASIC to FPGA, you will come across all the categories, right? With respect to the pipeline, with respect to the clock. But whereas if you are moving from FPGA to ASIC, so I think moving on from FPGA to ASIC, it is it is a time consuming, right? We see there are many disadvantages that if you are switching on you're designing from FPGA to ASIC, because like FPGA is very easy to it is very simple, very easy to construct, whereas ASIC is a bit complexity. We can see more number of complexity can be occur in ASIC. So rather moving on from FPGA to ASIC, better we can make a choice to move from ASIC to FPGA. Okay, I hope you all understand this particular topic based on the problems that you arise in the ASIC and the problems that you arise in the FPGA. If you compare both FPGA and ASIC, the complexity in terms of the complexity, time, clock, and all the logic synthesis, I can say that the designing in FPGA is more convenient. Okay, I think you have understood this topic, and thank you.
Like, share and subscribe. Hit the bell icon for more updates.